Today's physics drill is going to be kind of difficult. So we've got this problem here, and we're going to try to figure out which topic it is from this list of topics over here. So let's just see what it is. A particle with mass m is confined to a one-dimensional region between x and L. So we're already thinking particle in a box. Uh, Particle in a box. Hmm. Probability of each outcome. Hmm. Particle is prepared in a state proportional to sign. What values can be obtained in an energy measurement, and what is the probability of each outcome? Okay, two topics. Definition. Localized wave packet moves in the x direction through a region of space where a time-independent influence causes the phase to change. Leave its spatial probability density unchanged. Um, After the packet exits the region, explain whether any measurable change occurs in the particle's average velocity and what observable effect remains. Um, this seems like continuity or flux. Observable effect remains along with wave packets. Operators and expectation values. So I guess momentum and velocity. Are those expectation values? Momentum is this, velocity is that. Yeah, momentum is definitely operator, so we kind of already know that. Okay, next question. Two topics again. Two different measurable quantities cannot simultaneously have definite values. If one quantity is measured and found at a specific value, what can be said about the possible outcomes and statistical spread of a subsequent measurement of the other quantity? Oh my god. Sounds like expectation values, maybe commutators. Um, that it? Expectation values and commutators. Alright, next question. Two topics. Particle is confined to move along a line and is initially prepared in a stationary state. Second here. Um, Probability density does not change in time at a later moment. The sudden change is made to the conditions that allow motion. Yield multiple possible values. Determine what those possible values and how the probabilities are fixed by the initial state. Um, So I think that it would be Schrodinger equation, maybe bound states. I don't really know. Confined to move along a line, initially prepared in a stationary state. Probability density is a later moment of sudden change to make recognition, but define a rapid motion after which a measurement of the particle's energy can yield multiple possible values. Expectation values? Schrodinger equation and bound states, so not the expectation values. Eigenstates are not expectation values? Eigenvalues? That's interesting. Hold on a second. So eigenvalue is one measurement. Expectation is the average of the eigenvalues. Oh, that's kind of interesting. Something I probably should put in this quantum physics section here. So we're kind of talking about, yeah, the average of the observable, um, repeated eigenvalue measurements. Boom. So this expectation value is the average of the observable when you take a repeated eigenvalue measurements. Pretty chill. Let's do a couple more. Hold on a second. Make sure to draw from list topics. Here we go. One for electromagnetism. So localized burst of electromagnetic energy propagates through empty space toward a perfectly absorbing object. This immediately makes you think pointing vector. As the burst is absorbed, the object begins to move. So electromotive force? Maybe not. That's EMF, isn't it? So I don't think that's correct. Using the fields before enough observation to determine how those mechanical motions are accounted for. Momentum in the fields. Yeah, I didn't think the electromotive force was in there. But what's... Huh. Yeah, exactly. I was like, hold on a second. Isn't it just voltage? So actually the electromotive force is actually just voltage. Yeah, let me sort of mark that down because it can get a little bit confusing. Electromotive force is more like a voltage. So why don't we just say electromotive voltage? What? Okay, next question, two topics. Yeah, still. We should combine one with electromagnetism and one with, like, combine them. That would be crazy. Okay, a long conducting loop is initially at rest, empty space, no currents flowing. Over an infinite time interval, external conditions are changed so that the currents appear and electromagnetic fields build up around the loop, in which everything settles to a steady state. So far, I'm thinking auxiliary field H. During this process, the loop experiences a mechanical torque and begins to rotate. Yeah, interesting. Account for how this rotation arises using only fields present in angular momentum in fields. Maybe this, maybe this, maybe that. Okay, so angular momentum in fields and Maxwell equation. Uh, so the H field is not involved. Hmm. I guess because it's not magnetic matter, it's just okay. Yeah, the H field and the B field is a little bit difficult to understand. I guess it's just a magnetic field. I guess the H field is just a magnetic field, including M, or adjusted by M. Okay, next question. Combine one topic from EM and one topic from quantum. Again, no hints. Okay, here we go. A particle prepared in a coherent superposition has two spatially separated path travels to regions where all measurable forces vanish along both paths. Then the paths are recombined to produce an interference pattern. It is observed that changing a controllable parameter associated with the surrounding environment shifts the interference fringes, even though the particle never enters a region where its trajectory is deflected. What is happening? Explain what determines the phase difference responsible for the shift and why the particle's motion remains force-free. So there's a phase shift, particle's trajectory doesn't get deflected, and, and no force. Um, so I guess we're dealing with Lorentz force, the momentum in fields, maybe, and then maybe also spin. Let's see. This one was a hard one. Vector potential in the Schrodinger equation. Well, why? How did we know that it was the vector potential in the Schrodinger equation? Well, quantum phase evolution. Quantum phase evolution is Schrodinger equation? Oh, okay. Let's go take a look at that then. Schrodinger equation, and this can govern phase evolution. I'm sure it governs other things too, though, so I don't want to get too precise on them. And then, how did you know how did you know the vector and the vector potential? And how did you know it was the vector potential? Vector potential can change the quantum phase without a force, huh? That's weird. The vector potential uh, causes gauge transformations without changing the fields. Well, not really without changing the field, but without force. Okay, okay, okay. Okay, so I think what we have to do, sorry, we have to do a gauge transformation. And this is electromagnetism, so it's not anything crazy. The question is, did I put any gauge transformations over here? Uh, yeah, the vector potential is right here. So the vector potential, say, can become A plus some gradient of x here, I guess. This is not the same as that. So, uh, what can I write here? This. Oh well, just too many symbols, too many symbols. Not enough symbols, too many things to write. Then we have this, which becomes this minus this, which leaves the fields unchanged. Gauge transformations, which don't take any forces. That, and I guess we have this. Fields are unchanged, I guess. Okay, gauge transformations are phase changes. Phase change without a force. Okay, so yeah, interesting. All right, all right. Whew. Okay, this is a tough exercise, and we've been going here for a while. So